name is Dr. Esther Trufan, and in this video, we are going to explore the energy associated with electromagnetic radiation. It is important that we remember electromagnetic radiation can be emitted or absorbed in the forms of photons, and those photons have these small packages of energy. And these discrete entities or discrete packages of energy are called quanta. This is the energy associated with a photon, which is the smallest energy that can be emitted or absorbed. Now, according to Planck's law, there is a direct relationship between energy and frequency. The higher the frequency, the higher the energy associated with it. And the relationship is connected through Planck's constant. The value of Planck's constant is 6.63 times 10 to the negative 34th joules times second. And it makes sense to have this unit associated with the constant because the unit for frequency is the per second or hertz, and that cancels out the second in the constant, leaving us with the unit of joules, which is the unit associated with energy. So for energy, we have joules, and we get it by multiplying joules times second by the per second. So second times per second cancel out, and we're left with joules. We can also connect the energy of a radiation to its wavelength because there is a direct relationship between frequency and wavelength. So in our first expression, we have Planck's law, which says energy is the same as Planck's constant times the frequency. In the other expression, we have the inversely proportional relationship between frequency and wavelength through the speed of light. And then if from here we say that the frequency is c over lambda, then we can place, instead of nu in Planck's law, the c over lambda function, and we get energy equals h, which is Planck's constant, times c, which is the speed of light, divided by the wavelength. And this way we find that the higher the energy is, the lower or shorter the wavelength will have to be. There are a couple different ways in which we can utilize this information. The simplest kind of problems that we can come across is the utilization of the electromagnetic spectrum to compare two different types of radiation based on their energy. At that point, we need to make sure that we are looking at the appropriate scales. If we have the frequency scale provided, then we know that energy and frequency are directly proportional, and the energy of the radiation increases in the same direction as the frequency increases, which means in this case, from right to left. On the wavelength scale, we find that there is an inversely proportional relationship between energy and wavelength. And so the energy of the radiation will be larger the shorter the associated wavelength. And so we find that the energy increases in the opposite direction of the wavelength increase. To apply this in the context of a couple of problems, we have first a connection between frequency and energy, because this electromagnetic spectrum comes with only the frequency scale. If we are to compare microwave versus X-rays, then the first thing we have to find is the relationship between the two frequencies. Microwave has a frequency of 10 to the power of 10. X-ray has a frequency of 10 to the power of 18, which means that whichever one of these two has the higher frequency, it will also have the higher energy. And that means X-rays are the higher energy radiation among these two. Let's look at the same problem, but now from the perspective of the wavelengths. Our electromagnetic spectrum provides the wavelength of all the different types of electromagnetic radiation, and we know that if we have a high energy, then we should have a short wavelength. We have microwaves and we have X-rays. Microwaves have an approximate wavelength of 10 to the minus second, and X-rays have an approximate wavelength of 10 to the minus 10. Of these two, the shorter wavelength belongs to X-rays, which means that the higher energy will also belong to X-rays. So regardless of whether we're using the frequency or the wavelength side of the electromagnetic spectrum provided, both of those should lead us to the same conclusion regarding the energy, that the higher energy belongs to the higher frequency and correspondingly the shorter wavelength radiation. Another type of problem that can come up is to determine the energy if we are provided either the frequency or the wavelength of a type of radiation. Here we have a radio wave with a frequency of 89 megahertz. Before we can do any kind of manipulations or use Planck's law, we have to convert our megahertz into our base units for frequency. So in step one, we take our 89 megahertz and we convert it to hertz. We multiply by our conversion factor that has a 1 megahertz on the bottom and 10 to the 6th hertz on the top. The megahertz will cancel and we will have 8.9 times 10 to the 7th hertz. Once we have our frequency, it is time to apply Planck's law. In this expression, almost everything is known except the energy, which is our task to calculate. Energy equals, we take Planck's constant, 6.63 times 10 to the negative 34th joules second, and we multiply it by our previous calculation, 8.9 times 10 to the 7th, and here we have per second. This allows us to simplify our units. Second divided by second cancels it out. And now we are left with units of joules, and we need to add the value associated with that, which is 5.9 times 10 to the negative 26th joules. If we can do this calculation knowing the frequency, we should also be able to do this using the wavelength. So in this problem, we have the wavelength of a radiation provided as 515 nanometers. In the first step, we always convert to the base unit. 515 nanometers get converted to the base unit by multiplying by the conversion factor. On the bottom, we place 1 nanometer. On the top, we put 10 to the negative 9th meters. This will result in 5.15 times 10 to the negative 7th meters. Once we have our wavelength expressed in meters, it is ready to move on to Planck's law, as it is revised and rewritten to include, instead of frequency, the wavelength value. Here we have it. Everything is known but the energy that we need to calculate. So the energy will be equal to Planck's constant, which is h, and has a value of 6.63 times 10 to the negative 34th joules second. Then we multiply this by the speed of light, which is 3.00 times 10 to the 8th meters per second. And we divide this by the wavelength expressed in the base units we just determined. 5.15 times 10 to the negative 7th meters. The meters will cancel, and the per second and the second will also cancel. This leaves us with units of joules at the end of our calculation. And the value will be 3.86 times 10 to the negative 19th joules.